We have always been builders. That is the nature of human imagination. From the memory of a distant imprint in an ancient cave to this present age of space, we have relentlessly applied our skills to shape the world in which we live. We have progressed because of our determination to achieve what we believe we can accomplish. We have continued to build upon our science, creating an ever more complex array of tools with which we can explore and develop our environment. Tools are instruments of vision, and it is with these hands that we have used them to build a future in space. Until now, the European Space Agency's contribution to spaceflight has centered upon unmanned space vehicles. It was European science that first opened the gateways to the age of space earlier this century. Now, European skills will be used in a concerted effort to develop space as a resource of the future. From the confinement of our small planet, we have looked through the ages to the stars. To cross this frontier, we must build, drawing upon all our acquired skills to shape instruments with which we can refine and extend our knowledge. We recognize that space represents an immense resource for the ingenuity of man. But to develop the potential of space, we need new tools, new extensions of the human hand. This is Spacelab, under assembly in the Integration Hall of Erno in the Federal Republic of Germany. Spacelab is Europe's stepping stone to a new industrial age. Until its advent, research in space was restricted to expendable vehicles involving large quantities of expensive hardware that could never be recovered. Because Spacelab has been designed to return to Earth after each mission, a new opportunity for manned research in space has opened. Now we can reuse equipment, modify our techniques, and develop new approaches to the use of space. More than 50 European industrial contractors responsible to the European Space Agency shared in the development of Spacelab and have engaged in activities ranging from the construction of the manned pressurized module to the integration of scientific instruments and the assembly of unpressurized pallets. For the first time, scientists who have not necessarily been trained as astronauts will be able to work in space. They're called payload specialists. 3 European scientists are included in the immediate Spacelab program. Dr. Claude Nicolier, a Swiss astronomer, will work as a mission specialist. 2 other scientists, Dr. Ulf Merbold, a German physicist specializing in solid-state physics, and Dr. Ubo Ockels, a Dutch nuclear physicist, are also included. They were selected from thousands of applicants to train for the first Spacelab mission. The objective of the program is to provide in space the facilities and the comforts of a well-equipped Earth-based laboratory. On the first mission, the payload specialists will execute some 70 different European and American experiments. In addition to pre-planned operations, they will be able to operate equipment manually, reacting to unexpected conditions and changes using their own initiative to obtain the greatest scientific yield. Spacelab will breach the barriers of sustained scientific research in space. To develop the potential of space as a resource of the future, we need new insights into this environment. These cannot be obtained on Earth. Spacelab's orbit will position it above the atmosphere. It will provide access to the unique conditions of space: very low gravity, high vacuum, high energy radiation, and large volumes of ionized gases. The variety of investigations is considerable. Onboard furnaces will be used to heat material samples to study their changes in weightlessness. It is already well known that the processes of physical change in most materials are quite different when the governing force of gravity is removed. But the scientific potential and application of this has yet to be fully explored. Much of the scientific equipment has been specifically designed for Spacelab. This helmet, which will be used for measuring vestibular responses, represents a miniaturization of a range of bulky equipment used at present in medical clinics on Earth. But not only will this technology be used in space, it is already being used in European hospitals, because its unique design means that it will extend the research options for medical investigators on Earth. Spacelab will elicit an enormous quantity of new data. This will be transmitted directly or returned with the laboratory in the form of magnetic tapes, photographic film, life science specimens, and material samples. The results of these investigations will contribute significantly to the understanding of the real potential of space to man. This information will be made available to scientists all over the world for evaluation and for the formulation of research for future missions. It has taken the European Space Agency a relatively short period of time to develop Spacelab. Its construction parameters and its far-sighted ambitions are both unprecedented in Europe. But by the end of 1981, the preliminary integration of the system was nearing completion in Germany and being prepared for delivery to NASA in the United States. Spacelab has been designed as a modular structure that can be used over and over again. The concept is based upon a manned, pressurized laboratory and a series of pallets that will support instruments designed to be exposed directly to the space vacuum. Module and pallet function together, and in this example, form the configuration of the first mission. Within the manned module are a series of removable racks. The first two racks contain the Spacelab subsystems, which include controls, life support, electrical power, computers, and equipment for communications with the orbiter and Earth. It also contains a workbench, data display unit, and keyboard for communications via the computer to the experiments. The remaining racks are for experiment equipment and also may contain facilities such as furnaces, incubators, centrifuges, a fluid physics module, which are available to all Spacelab users. In addition, stowage space is available in overhead containers under the floor or in the racks themselves. The main part of the life support equipment is housed under the floor of the subsystem module. This essential includes a high degree of redundancy. On the roof, there is a scientific airlock. It provides access to the space vacuum for a number of specific experiments, which can be prepared or tended in the pressurized environment. There is a high-quality optical window, which allows for accurate visual observations for scientific purposes, and viewing ports, one of which overlooks the pallet. Spacelab will be returned to Earth with the orbiter after each flight. It can be reconfigured to meet the varying demands of each different mission with its own particular research objectives. The manned module can be shortened or dispensed with altogether, and instruments can be mounted on a series of pallets. The essential Spacelab electronic components are then housed in an igloo, which provides a thermally controlled, pressurized environment. A variety of ancillary equipment will be provided as part of the Spacelab services for users. One important example of this is the instrument pointing system, which is mounted on a pallet and provides a high-accuracy pointing and stability base for large research instruments such as telescopes. The modular concept leads to many different configurations. The first mission will use the long module plus pallet. After integration in Bremen, the flight unit for the first Spacelab mission is transported to NASA's Kennedy Space Center in Florida for final integration with the payload and the shuttle orbiter Columbia. In the operations and checkout facility, European and American engineers now work together to ensure that Spacelab will become a functioning part of the shuttle orbiter. Computers must interface. Data relay routes must be compatible. Life support and experiment control systems must be tested. The European experiments will already have been integrated in Europe, but now they must be brought together with a contingent of American experiments to function as integrated parts of Spacelab and the shuttle. This is a meticulous procedure, and it will be many months before the final assembly is ready to be placed in the payload bay of the Columbia. Once this is completed, Columbia and Spacelab will be coupled to the external tank and the solid rocket boosters for their journey into space.
1 for redundant set sequencer start. T-minus 20 seconds and counting. The SRB nozzles have been moved to start position. Coming up on 10, T-minus 10, 9. We have go for main engine start. We have main engine start. Minus 3, 2, 1.
2 minutes after the launch from Cape Canaveral, the 2 solid rocket boosters will burn out and separate. They will be jettisoned into the Atlantic Ocean for recovery and reuse. On board the orbiter, the crew will monitor trajectory information, and the orbital maneuvering system will insert Columbia into a pre-planned low orbit, some 260 kilometers above the surface of the Earth. The payload bay doors will slowly open, and Spacelab's first mission will begin.
For the first time, she's been deployed, working great. We have done all the way.
This flight will last for 9 days.
Waiting for the starry data tank to be over to get back into it and do the THC.
The American and European payload specialists will crawl through the access tunnel that connects the orbiter with the manned Spacelab module. A thermal shield which blankets critical structures will provide essential protection from the extremes of temperature that will be experienced as the orbiter circles the Earth every 90 minutes.
Okay, go ahead.
On its first Spacelab mission, the Columbia will carry a crew of 6, 2 pilots, 2 mission specialists, and 2 payload specialists, including the European scientist Dr. Ulf Merbold and the American scientist Dr. Byron Lichtenberg.
Okay, I understand.
Merbold and his European and American colleagues have undergone a long period of training for the Spacelab program. They must be familiar with every piece of equipment and each experimental procedure, for once in orbit, the success of the mission will depend upon their skills.
We have completed step, the procedure on page 1-26.
Inside the pressurized module, the scientific program will be activated. They will work to a rigorous schedule that has been prepared over several years. None of Spacelab's valuable time must be wasted. Not only must the experiments be accurately executed, but much of the vital information must also be relayed to Earth as it becomes available. This will be transmitted from the orbiter to ground-based data receiving stations, either directly or via the tracking and data relay satellite system. Data will be collected and eventually distributed from the Goddard Space Flight Center in the United States.
Okay, super. Thank you much. Dan, we appreciate that.
Spacelab has been designed to become an international research facility, available to scientists and commercial users drawn from all over the world.
You bet.
From the Payload Operations and Control Center, scientists on Earth can communicate with the Spacelab crew by voice and closed-circuit television links. This access to the European-made space laboratory will allow them to monitor the progress of experiments and to intervene by either instructing the crew verbally or by sending automated commands to the onboard computers.
A lot of teleprinter messages that have come up over the night. The one we'd like you to look at first is 35 Alpha.
After completion of its first 9-day mission, Spacelab and the Columbia will prepare for the re-entry maneuver. As the orbiter is drawn by the gravitational field of the Earth, It will re-enter the atmosphere at an equivalent ground speed of nearly 27,000 kilometers per hour. Protected during re-entry by its shield of thermal tiles, the Columbia will make its final approach to the runway at Edwards Air Force Base. On later missions, the landing will be at Kennedy Space Center, a few kilometers from the launch tower. Spacelab is the first reusable manned research laboratory in the history of spaceflight. Over the course of the 1980s and the 1990s, together with the Space Shuttle, it will undertake many different missions, using its full range of configurations. It is a tool, an instrument of vision. With its multiplicity of facilities, we will begin to explore the real potential of space. We will look into the depths of our galaxy and beyond, using Spacelab as a pathfinder for developing new astronomical instruments, with which we will begin to unravel some of the mysteries of the universe. Even the behavior of our own star, the Sun, is only partially understood. With Spacelab's capacity to prove new research technologies, we will develop a new scientific theater. We will look at our own planet in different ways, studying the behavior of the atmosphere, learning how it sustains itself, how it's damaged, and how it may be protected. With new remote sensing techniques developed by Spacelab, we will map the surface of the Earth from space with an ever-increasing sophistication, locating new resources and hidden pollution hazards. Spacelab will provide life sciences on Earth with new insights and new equipment. We will use microgravity to unlock some of the secrets of the human body. We will learn more about the human immunological system, how cells divide and replicate. We will learn more about the human vestibular system, how our sense of balance is controlled and damaged. This will provide us with new perspectives into disease processes on Earth, and eventually we will be able to produce new medicines made in space, new vaccines of a purity that cannot be obtained on Earth. Freed from the constraints of gravity, matter behaves quite differently in weightlessness. Crystals form with a high degree of perfection. Containerless liquids may be manipulated to produce pure samples, and high-strength, lightweight materials may be prepared. It is for this future that Europe has built Spacelab. From the knowledge that we will acquire, we will create a template for an age that will fully exploit the potential of space. An age that one day will culminate in orbiting factories and new technologies to probe the darkest recesses of the universe. Our fascination with space is as old as man himself. Every society throughout history has looked to the stars, and our achievements represent thousands of years of endeavor and exploration. This age of space, with all its potential, started with the time we first began to leave our imprint upon this world with the unwritten words, "I am man. With these hands, I built a vision."